Hi students, in this lecture we are going to discuss previous IIT problems. See the first one. This is a 2011 advanced problem. Let us see what's the data given. A metal rod of length L and mass M is pivoted at one end. A thin disc of mass capillum and radius capillar is attached at its center to the free end of the rod. Consider two ways the disc is attached. Case A, the disk is not free to rotate about its center, and case B, disk is free to rotate about its center. The rod disk system performs SHM in vertical plane after being released from the same displaced position. Which of the following statements are true? So this is now given data, and in this we have to focus case A and case B. Case A. Case A, disk is not free to rotate about its center. Case B, disk is free to rotate about its center. And you can see when disk is free to rotate, then motion of disk will be, it is a pure translation. I am repeating, when disk is free to rotate, when motion of disk becomes pure translation. In such a case, we can replace the disk with a point mass at its center of mass. Okay. And when disk is not free to rotate, then motion of the disk is taken as motion of center of the disk and rotation about center of the disk. Combination of these two. Let us see options. Given that a restoring torque in case A equal to a restoring torque in case B. So here we can see restoring torque is because of weight of the rod and because of weight of the disc, and these two are not changed. Okay. So I am writing here. You can see torque. Torque is the same in both cases. And see that torque is mg sine theta into L by 2. This is because of weight of the rod. Because here we are taking weight of the rod is passing through its center of mass. That's why it is L by 2. Okay. Next. mg sine theta into L. This is due to weight of the disk. So this is not depending on how disk is fixed. That's why torque is the same in both cases. Okay. But coming to case A, they mentioned that disk is not free to rotate. Therefore, motion of the disk will be motion of center of the disk and rotation about center of the disk. Now see carefully here. Then what we are doing is in case A, ml square by 3, that is moment of inertia for the rod about one end, mr square by 2, rotation of the disk about its own axis. So taking mr square by 2 plus ml square, because we are taking translation of center of mass of the disk. So this is I value in case A. Okay. And if you see case B, for the rod there is no change, ml square by 3. But coming to for the disk, since disk is free to rotate, it is a pure translation. So we are replacing the disk with a point mass at its center of mass. That's why only ml square. That means in second case, I value is less. When I value is less, alpha is more. I am writing here tau equal to I into alpha. Tau value same for both the cases, but I value is now less. It is less in case B. Therefore, alpha B is more. Alpha B more means omega B is more because omega proportional to alpha. Okay, that's why answer is option A. It is correct. And next we got here omega A less than omega B. Omega A less than omega B means this option D. So correct one are A and D. Okay, that is the answer. See next problem. So you can see now this is 2013 advanced problem. Just see the question once. A particle of mass m is attached to one end of a massless spring of force constant k lying on a frictionless horizontal plane. The other end of the spring is fixed. The particle starts moving horizontally from its equilibrium position at time t equal to 0 with an initial velocity u0. When speed of the particle is 0.5 u0, means velocity becomes half, it collides elastically with a rigid wall. After this collision, right? See options. Option A, the speed of the particle when it returns to its equilibrium position is u0. So this we can say directly because by using energy conservation, it collides elastically. Given collides elastically, no energy loss. Therefore, when it returns to its equilibrium position, no change in speed. So option A is correct. Next, the time at which the particle passes through the equilibrium position for the first time is. So coming to B, see the solution part. So I'm writing here V equal to U naught cos omega t. So why we have taken cos omega t means when t equal to 0, velocity equal to u naught. Okay. Now see, velocity is a half of initial value, u naught by 2. That is equal to u naught cos omega t. That implies t equal to, so cos value becoming half. Cos half means omega t value must be pi by 3. Therefore, t value pi by 3 omega. Right. I am making diagram here to make it clear. There is now a wall, rigid wall, spring and a block. Velocity given u naught. There is a wall here. There is a wall. When it collides with the wall, its velocity u naught by 2. U naught by 2. Okay. So we are getting time taken for making collision. So from mean position to make collision time taken is now t. To come back after collision to mean position again same. Therefore, the time, the time after which particle passes through the equilibrium position for the first time is I'm taking as T1. T1 equal to 2T. Okay. That is 2 pi by 3 omega. And in the place of omega, you can write, it is as usual 2 pi by 3. 2 pi by 3. In the place of omega, I am writing now K by M. Okay. Sorry. I have taken reverse, right? This becomes omega value root of K by M. Therefore, this becomes a root of M by K. Okay. That is answer. So in the options, that is not there. Okay. Right. Now see next one. Option C. The time at which maximum compression of the spring occurs is the time at which maximum compression of the spring occurs is. Now see diagram carefully. After time t1, it comes to mean position. From mean position to have maximum compression, it is nothing but extreme position. It is nothing but extreme position. To travel from mean position to extreme position, time taken is t by 4. Okay. Therefore, now total time taken, it is how much? It will be, I am writing here, it will be t by 4 plus 2t1. Okay. And that comes how much means that is equal to, see how much we get, t by 4 plus, and you can see 2t1 is nothing but t by 3, right? So t by 4 plus t by 3. So this is equal to 3 plus 4, 7. 7 by 12. 7 by 12 t. And in the place of t, we can substitute now 7 by 12 in the place of t. 2 pi root of m by k. That is equal to 7 by 6 pi root m by k. So after this time, compression of the spring will be maximum. And see what's the answer given here. It is given pi by 3, sorry, 4 pi by 3. So answer is not matching. Okay. Right. Next, see fourth option. The time at which the particle passes through the equilibrium position for the second time is, passes through equilibrium position for the second time. Okay. Then see what happens. See diagram carefully. To come back to mean position for the first time, time taken is to t1, right? T1. Next, from here to left extreme, t by 4. From there to back, again t by 4. It is t by 2. How much? T by 2. So I'm writing here t1, t1 plus t by 2. Okay. So t1, that is 2 pi by 3 omega plus t by 2. That is now pi by omega. This is now time after which it passes through the equilibrium position for the second time, right? Not first time. Here I have to make correction for the second time. I am writing here. This is the second time, not first time. Second time. And see what is the answer given here. Yes, it is matching, right? Pi by 5 pi by 3 root m by k. So option A and option D are matching. So answer is, it is AD. Okay. Right. Now see next problem. This is advanced 2023 problem. Read the question carefully once. Two point-like objects of masses 30 gram and 20 gram are fixed at the two ends of a rigid massless rod of length 10 centimeter. This system is suspended vertically from a rigid ceiling using a thin wire attached to its center of mass as shown in the figure. The resulting torsional pendulum undergoes small oscillations. The torsional constant of the wire is 1.2 10 power minus 8 Newton meter per radian. The angular frequency of the oscillations is the value of n is. So it is very simple question. We know time period is 2 pi root I by c. Now you are given angular frequency. So omega value root of c by I. The value of c is given. So we have to calculate now I value. And it is given that it passes through center of mass. I am drawing diagram here. Length is given 10 centimeter. Mass is given 20 gram and 30 gram. So first we have to focus center of mass location. Suppose one is x1, this is x2. Then I can write x1 value means distance of center of mass from 20 gram. See how much it is. X1 equal to 10 into x1 equal 10 into 30 by 50. Means it is m2 r by m1 plus m2. Okay. See how much we get. 0, 0 gets cancelled. 30 by 5, that is a 6. So 6 from 20 gram. Okay. 6 from 20 gram. When it is 6 from 20 gram, it is a 4 from 30 gram, right? So m1 x1 square plus m2 x2 square, that is I value. And once we get I value, now substitute the value of I in this one and a C value is given. Then we get directly n, right? N value how much? It is a 10. Okay. So it is a very direct and simple question. And 2023. Right? See next problem. This is very interesting problem. Somewhat difficult to solve in the examination time. See what is given. A block of mass 2m is attached to a massless spring with a spring constant k. This block is connected to two other blocks of masses 2m and m using two massless pulleys and strings. The accelerations of the blocks are a1, a2 and a3 as shown in figure. The system is released from rest with the spring in its unstretched state. The maximum extension of the spring is x0. Which of the following options are correct? Neglect friction, right? Right, see options given first. So first option is maximum elongation rate that we have to calculate. Second one, when extension is x0 by 2, speed of the block connected. Okay. Next, a relation among A1, A2 and A3. And fourth option, when extension is x naught by 4, magnitude of acceleration of the block, right? Do one thing first, we can verify option C directly. Okay, see how to verify. So here, let us take tensions. Tension, suppose this is a T, then this also T, right? Then in this part, tension becomes, this becomes 2T. Then we can write directly 2A1 is equal to, it is A2 plus A3. Remember here, directions are given. That's why here A3 given down, A3 also down. That's why the equation becomes 2A1 equal to A2 plus A3. Okay. And if you see option C, A2 minus A1 equal to A1 minus A3. That means 2A1 is equal to A2 plus A3. So option C is correct. Okay. So option C is correct. Next, let us see remaining options. How to calculate maximum elongation of the spring. So here what I'm thinking is that when elongation is maximum, speed must be equal to 0, right? Let us focus now this block. Okay. Force equation. Force equation I can write 2t minus kx. We can see solution part here. First I'm writing force equation for that block, which is connected to that spring. That is 2t minus kx. I am drawing here free body diagram. Free body diagram. Its mass is 2m. Okay. Its mass 2m. Tension 2t. Spring force. It is now kx. So net force equal to 2t minus kx equal to its mass is 2m into A1. Okay. Now to find tension, what I'm doing is I'm using the result which we got in case of Atwood machine. That is, in case of Atwood machine, I am drawing here. In case of Atwood machine, if your mass is M1 and M2, M1 and M2, tension equal to 2M1 M2 by M1 plus M2 into G. So I am going to use now that result in this one. So here we have taken 2 M1 M2 by M1 plus M2. But in the place of G, I have taken G minus 7. The reason is that this pulley is now moving down. I am showing here. The pulley here, it is moving down with acceleration A1. Okay. That's why there we have taken the place of G minus 7. Now substitute equation 2 in equation 1. We get 8m by 3 into G minus 7 minus kx equal to 2m into A1. Now rearrange this. Rearrange this to get A1. See what we got here. A1 equal to minus something into x minus 8mg by 3k. So this is of the form minus omega square into displacement. This entire one is corresponding to displacement, entire one. Okay. And in that x corresponds to elongation of the spring. Or what we can do is, I am showing a diagram. Let us take this position of the block when spring was unstretched, taking that as origin. Okay, taking that as origin. Then x coordinate becomes elongation of the spring. Okay, x coordinate becomes elongation of the spring. Then see what we get here. Then here x becomes x coordinate, and this is now x coordinate corresponding to mean position, because when x equal to this value, acceleration becomes 0, and we are knowing that acceleration is 0 at mean position. Okay, therefore I am writing here, so you can see, we can say that mean position is at x equal to 8 mg by 3k, because for that x value acceleration is 0. So we got now x coordinate for mean position. And we have one more condition. Block starts from rest when there was no compression, no elongation. That means x equal to 0 corresponds to one extreme position. I am repeating, x equal to 0 corresponds to one extreme position. Why extreme position means? Because their velocity equal to 0, right? So when extreme position is x equal to 0, corresponding to mean position 8 mg by 3k. That means amplitude is 8 mg by 3k. That is what we can see here, 8 mg by 3k. And one extreme is x equal to 0. I am drawing diagram here. One extreme is x equal to 0, x equal to 0. And coming to mean position, 8 mg by 3k. 8 mg by 3k. Then other extreme will be x equal to 16 mg by 3k. Other extreme means where velocity equal to 0. That means maximum elongation. Maximum elongation is equal to 16 mg by 3k. Okay, right. Now see options. First one, maximum elongation is 4 mg by 3k. That is wrong. When spring achieves an extension of x naught by 2 for the first time, speed of the block. Remember, x naught is now maximum elongation. X naught by 2 corresponds to mean position. At mean position, velocity equal to, it is a into omega, right? Okay. And this is not matching with that, because a value, it is 8 mg by 3k, and omega value is now, see, we got here omega square is 3k by 14m. So answer is not matching. Okay, right. Next, so option B not correct. At an extension of x naught by 4, magnitude of acceleration of the block, that we can verify directly from equation 3. Okay, in the place of x, take x naught by 4. X naught we got how much? X naught, it is 16 mg by 3k. Now take, there it is x naught by k. In this, take that value, then acceleration is not matching with the given value. So this is also not correct, right? Like this, we can verify all options. Okay.